Hello and welcome back to Calculus 3, section 13.3, double integrals on polar coordinates. Yeah, that's going to be a challenge over there. Those are lost, by the way. Apparently this is not working yet, so let's see. Let's try connecting one more time.
These are probably all of them, but like, you know.
Oh, thank you.
Oh, yeah.
Here we are with
Well, I'll make sure I put them in a bag tonight, so. I mean, if it makes you feel worse, I gave Calculus 1 their exams back this morning.
Yeah, thank you.
It does make, yeah, that does make.
I actually don't really care.
Good.
I care about them, so
Coordiantes.
it's kind of fun.
Did you put the grades in the grade book?
It's not a grade book. Yeah, do we have a grade book?
I had to.
No.
Coordiantes. This is in Spanish over here. Let's move it, or Italian. Okay, fine.
Have you done a class prep? So, like, have you looked through those yet? Though?
No, they're right here.
No, I.
Oh, you didn't keep the checks next to the titles in the syllabus?
No, I'm dumb.
Well, we don't need to know that.
Wait, did you?
You do?
Okay, what class prep did you take back?
Now I have to start this all over again. All right. Stop. Hello and welcome back to Calculus 3, section 13.3, double integrals and polar coordinates. So now we are moving away from rectangular domains that are on x, y, and going into the polar domain so that we can work with rounded objects and figure out the volume and so. So 13.1, your region R, since annoys some of you, is a rectangle going from A to B and C to D, and then your integral limits were A to B, C to D, or the other way around, C to D, A to B, depending on what you had. In 13.2, we had regions where, let's say, you have a linear line and the polynomial intersecting, let's say, at A and B. So we had A to B. Well, I should write the rest because it's important that this is dy dx here if I use this order. And then for the second one over here, we have g of x in the lower limit, f of x in the upper limit, and then we have something over here, and we have, again, dy dx. Now, the next lecture, which is what we are going to look at now, is the lecture where we are going to have a polar domain. Polar domain is in a circle, and we know that for polar domain coordinates, the point is given by r comma theta. So it's a radius r that you swing about certain angle theta, which gets you to the point r comma theta. You also learned in your Calculus 2 class, I hope, that you can find the area of the polar region using, yes, using the formula 1/2 alpha to beta of f of theta squared d theta. Now, this f theta over here is actually, from knowing the pre-calculus of the polar coordinates, r is equal to f of theta. So theta, the angle, is the input, and r would be the output. It works a little bit different than the regular functions, but it works for all purposes here. So now we want to use, and before I jump to the next part, also note that your integral here is two-dimensional because we are getting the area. You have f squared. Now that f squared is actually r, and these guys are angles which will contain pi. So you see that this is r squared times the integral for d theta is pi. So r squared pi, yep, that's the area of the circle, so that sounds good. We also see that both dimensions are within f of theta squared. This is not a dimension, right? For your dx dy, both of these were dimension, right? So you had the 2d when you write this as a dA. But you have to understand that theta is a ratio between, right, radian measure, which is any angle, is a ratio of the arc length and the radius. And those units cancel completely. So this is a unitless unit. Radian is a unit, and degrees are also unit that we use to measure the angles, but they actually are not units in the same sense as seconds are, or meters, or feet, because the degree is defined as a 360th part of a circle. There's no unit there. You're just taking something and dividing by 360. It's like a percent. Percent is not a unit. Percent is a 100th piece of something, of a whole. So a degree is 360th piece. It's like the same like percents, except it's based on 360. So both of our dimensions are in this part here. So now we want to develop the entire calculus double integral deal, where we can compute volume of objects that have base which can be fully described and easily described by polar coordinates. You really don't want to mess with a cone if you are with the double integrals with the x and the y. With polar coordinates, that's much easier. Cylinder is much easier. Everything is much easier that it's round like that. And you don't, so it complements. It doesn't really compete with the rectangular. It complements it and does different stuff. So we are going to now also, we are going to change the notion of a rectangular, of the word rectangular. Because for the first two sections, rectangular integral meant your domain is rectangle. And if it was a general region, that meant you had functions. We are still going to have rectangular for polar coordinates and general. Now, rectangular will refer to having numbers everywhere. So at this point in 13.3, we are going to diverge from the notion that rectangular means rectangle. And we are going to say that rectangular, when we call the integral rectangular integral, we mean that the only numbers in limits, no functions. And when it's general, it will have functions. So I'm going to write now two definitions for these integrals, which will have these one for rectangular and one for general. I'm just going to, all right, there we go. And then we have to talk about setting this up using the representative pizza slice. What happened?
We'll go from French fries to pizza slices.
Representative French fries next class, next lecture. We already did, yeah, but it's gonna be, yeah, better.
This one's with salt on it. The one tomorrow.
Seasoned.
Seasoned.
All right, so double integral over a region R of function that is r and theta. The area is going to be, and now for a rectangular one, we have angle on the outside and a to b on the inside of the function in terms of r and theta, and then r d theta. So we're going to box this one.
Is that always the order?
Yes. So this order is not going to change.
And what's the R?
And what's the r? The r is one dimension, and then dr 2 dimensions, and then you have the function, you can compute the volume. That r is, you see how this one is squared? This one is r times r times d theta. So now we are allowing one of these r's to change, and one r stays as is. I will draw some pictures. Hopefully we'll get better. Now, first I want to make sure that all of this is dimensionally sound. D theta has no dimension to it. dr has a dimension, and r has a dimension, so that's 2d, and then the function. So 3d, we can calculate volume. If I kick out this term, then I'm calculating area. Awesome. So dimensionally, everything works. We still call this rectangular polar, just oxymoron, but it is what it is, because all of these are numbers. Now let's take a look at example and try to understand what's happening here. If you ever put together IKEA furniture or whatever, you probably seen a washer. Washer is a metal thin metal disc. Well, actually, wait. You know, you don't know the CDs and DVDs, but you know the Blu-ray discs. That's all the same. So that's that. All right. So technically, we're talking about that. If I want to find the volume of something like this, well, I would need the surface area, and then I would need to multiply it by the thickness, right? So let's say that this is at 1, and this is at 3, and this scale is in centimeters, and then the thickness is 1 millimeter. Thickness equals 1 millimeter. What's the volume? Well, I need the area. Area is very simple to compute, right? You can calculate the area of the big circle minus the area of the smaller circle, and then just multiply by the thickness. Make sure you convert your units, right? Which I'm going to do. But you know, why simple if we can complicate things? Let's use the integral to compute this, because we can. The formula for the inner circle is simply r equals to 1. And the formula for the outer circle is r equals to 3. So now, if I want to set the area integral, and I want to use the double integral, well, I am going to use what I call a representative pizza slice. There it is. representative pizza slice d theta. We know that the string is r dr d theta. That doesn't change ever. And we just have to worry about the limits. Well, d theta on the outside, do I have a full circle? If the answer is yes, we are 0 to 2 pi. The inner radius, it's asking us where is the material, where is the mass of the disk. It's between 1 and 3. So you see that the inner integral, dr, is 1 to 3. And you can actually see that on the representative pizza slice, because representative pizza slice starts at the origin, shoots out, it hits 1 first, that's the lower limit, and then it hits 3 next, and that's the upper limit. So now if I'm solving this, integrate r to get r squared over 2, compute it from 1 to 3, and we still have d theta. You see that d theta will bring pi into the mix. So 0 to 2 pi, and now, good effort. There will be 9 halves minus 1 half d theta. That's 8 halves, that's 4. So 4 theta computed from 0 to 2 pi. And the whole area is 8 pi. Now that's 8 pi centimeters squared. Now, we are going to take the height, which is 0.1 centimeters, right? That was the 1 millimeter is 0.1 centimeters, and we're going to multiply 8 pi by 0.1, and the answer is centimeters cubed. So technically, this is 8 pi over 10, which is 4 pi over 5 centimeters cubed. And you can go and compute, right? So 4 times pi is about 12.5, and then you cancel that, and yeah. Yes.
The 0.01 centimeters is like the thickness that you gave at the beginning?
Yes.
And you have to do that, like that's not included in the integral then?
No, we can though, but it wasn't. You can include that if you create a plane that will fit in there, and then you would have a volume, right?
Okay.
So what I did is technically I previewed a lot of Calculus 2.
Is thickness the difference between the radius and outer radius then?
No, the thickness of the washer.
Like the
Yes.
E kind of, okay.
Yes, when you put it down flat on a pancake, what is the thickness?
Okay.
Right? This.
Yeah, I'm interested.
Now, we can compute the volume if we put the function inside. Generally, your grade dies with this r here. You forget that r, and then obviously the whole thing falls apart. So let's take a look at the paraboloid. So paraboloid, you can think of it as, some kind of umbrella. This is clearly not umbrella, but eventually it is that shape. And let's say you have that z is equal to, we pick, let's say, 4 minus x squared minus y squared. First of all, you see that this wraps around z-axis because it's z equals. I can wrap around the x-axis, and then you can say x equals, or y-axis, which would be y equals. So I would like to find the volume of this object, and I can do so by, well, first casting this, because I have to plug in function in terms of r and theta. So z is equal to 4 minus r squared. Now you might say why, and I will remind you from Calculus 2 that x squared plus y squared is equal to r squared. So if I factor a minus sign, right, 4 minus x squared minus y squared, if I factor out the minus sign, then I will have minus open parenthesis x squared plus y squared, and that's r squared. So I converted my formula, which was f of xy, into a formula which is z equals r theta. And the conversion for those are clearly the sets of formulas that you guys know. This is inverse tangent of y over x. So that's one set. And then the other set is that x equals r cosine y. And, sorry, x equals r cosine theta, and y equals r sine theta. So those are the conversion formulas from before. So now, as you can see, I can plug in 4 minus r squared and then times r dr d theta as a string. So this stays as a unit. It's added as a unit. We don't care what happens before it. This part gets added as a unit at the end. Limits. Is it a full circle around? Yes, it is. So 0 to 2 pi. And now we have to talk about the radius. Observe that the radius of this function, right, is changing as you go high. Radius over here and radius over here and radius over here are not the same value. So radius is one of the variables. Now, what are the two radii which bound the problem? Well, clearly at the top, radius is equal to 0 because it's just a point. And if you try to draw the radius at that point going outward, well, there's nowhere to go because it's just a single point. So on the top, right, we can see that the radius is equal to 0. Now, all the way on the bottom, when you intersect this, now this is where your level curves come in handy. When you intersect the shape with the plane, xy plane, so that you can see how far out it goes in terms of the radius, you will plug in a z equals 0. Xy plane is z equals 0. As soon as you plug in z equals 0, I don't care which equation you're going to use, you get that r is 2. Right? So the most that radius can go out is 2. And there it is. This will compute the volume. Do I have 3D? Yes, I do. 1, 2, 3 dimensions. D theta is not a dimension. So now we first rewrite this so that we can integrate. So 4r minus r cubed dr d theta. So now 4r, integrate that, you get 4r squared over 2 minus r to the 4 over 4. There is integral, parentheses, compute from 0 to 2, and we still have d theta to deal with. This is 0 to 2 pi. So integral 0 to 2 pi, this drops down to 2. So I have, when I plug in 2, it's 4, it's 8. Minus 16 over 4, which is 4. And then 0 just doesn't do anything there. So we have to integrate 4. So that's going to be 8 pi again. Not every answer is 8 pi. Sometimes we'll have 8 pi over 3. Yes? There is a fan over here, so you have to crank the volume up.
Okay, sorry. Okay, so the second limit of integration with the
Well, the radius, you see, if you are to shine the light on top of that umbrella or paraboloid, all you're going to see is this. You are going to see a shadow that it's filled like this. So what is our radii, right? I don't care whether it's top or the bottom, because would you agree that if I take this object and flip it, we'll have the same volume, right? So that will not change. This is one of the things that you now need to understand. Flipping the object upside down is not going to change limits at all. Limits are bounding the domain, right? What's going to change? The only thing that's going to change if you flip the object is the equation that goes inside, but that equation is just going to change. So it's going to be 0, and then you have to cut it off because you're flipping it now. But your equation inside changes, but your limits of integration will not change because it's still the same polar region. It's still the circle of radius 2. So it goes from 0 to 2, regardless. Well, now the way I looked at it is I said, well, at the top radius is 0 because I'm visual, and at the bottom radius is 2.
Wait, is that where it stops though?
Stops at the. It doesn't keep going. Yeah, it can go to infinity, sure.
If the shape was flipped around,
so that's why it's 2.
Well, it's 2, yeah, because it's just above the xy plane.
I see what you're saying.
Now, if you are to flip the object, it will look like this. And then you're cutting it at 4.
What's the function now for that object?
Well, it's going to be a plane minus the... So now, the issue is that you have a plane over here, and that plane is z equals to 4. You need to transform this plane into r theta. And you have the equation here, which says that z equals x squared plus y squared. And it grows without a bound, but this is its bound. So now you have to do over here that function f is just r squared. And over here, you have to transform this. What should we do? Well, no, it's just 4. So it's not friendly, right? We need to transform this into our r and theta. So z and z corresponds to, so z equals to 4. So function g on top is going to be 4.
Wouldn't that be the radius then too?
Do what?
For the last prop, you found radius by setting z equals to 0 because you knew from the shape of the object that that's where the biggest radius was?
Yes.
So in this case, the biggest radius is at z equals 4. So
yes.
You would plug in z into your equation and then
yes.
for r.
Yes, and you would still get 2.
And you'd still get 2, exactly.
That's, yeah, I was about to write that. There we go. And now you have your r dr d theta. And over here you have 4 minus r squared.
Wait, what's our z equation again now? What's our equation for z of this shape? Or the equation of the shape?
Well, it's the combination.
Well, the equation is x squared plus y squared, right?
Yes.
Yeah, okay.
So we have now two paraboloids that are intersecting here at z equals 8 minus x squared minus y squared, and z equals x squared plus y squared. All right, so yes. Oh, okay. I thought you had a question. So now I have my domain, and that domain is obtained when you shine the light on top of the object. Now that domain on the bottom will tell you the limits, because it's a circle that is full circle, right? That's 0 to 2 pi. And we can also calculate the radius, and radius will be 0 to whatever number we find. Now, how would you find this? Yes? No, we can do everything in one shot. What happened? Set, what is them? Yes. So in order to find the line for the domain, so that you can have your limits, you set the two equations equal to each other, and whatever comes out of there, that's going to be your, those are your limits. So now we have that 8 minus x squared minus y squared is equal to x squared plus y squared. This is going to be 2x squared plus 2y squared equals to 8. And then finally, x squared plus y squared is equal to 4. And we see that r is equal to 2 from there. Remember, no negative on r. It's a distance. So now what I'm going to do is set up the integral. Volume is double integral. We know that the outer integral is going to be theta, so 0 to 2 pi, because I want the entire thing. Guys, if you think of this as a watermelon, and you cut out a slice, so this is the top view. Now, this is going to look like Pac-Man, but it's okay. So this is a watermelon. I can make it watermelonish like this, let's say. So you're looking at the top view for the watermelon. Those limits are not 0 to 2 pi, because the slice is missing, right? So it could be pi over 4 all the way to 2 pi. And then you convert it back. So I have a full circle. Now my radius is again 0 to 2. Here's the $1 million box tip over here. It's top minus bottom. So this equation is on top. So we have 8 minus x squared minus y squared. Subtract x squared plus y squared. And finally, no, this is wrong. Yes, it is. I need this transformed into 8 minus r squared, and I need this transformed into just r squared. So we need to have those transformations, because we are supposed to plug in top minus the bottom. dr. No, d theta. So now if you work this out.
Why no RDR? Where did it?
What happened? Story of my life. So now it becomes 8 minus 2r squared, r d theta. So, okay, well, now we'll write both. All right. Now, dr d theta, there we go. Much better. So now we integrate in terms of r. Leave 0 to 2 pi on the outside. We haven't done anything yet with it. So r, that's r squared, so that's 4r squared. Minus 2r cubed dr d theta. Computed from 0 to 2. All right, good. I think.
Why did you integrate 2r?
Yeah, you gotta. Would it be 2r to the 4 over 4?
2r to the 4, so r to the 4 over 2.
Yeah.
Much better. All right, good. Well, that's why I have you.
Exactly.
So 4 times 4 is 16, minus 16 over 2, 8 d theta. That's 8, 2 pi, 16 pi. -8 is 8. Integral of 8 is 8x. And then you have 8 times 2 pi minus 0. So that's that. What is 16 pi? It's the volume of this shape. This shape contains two paraboloids. One goes up, one goes down, and when you connect them together, they create that kind of shape. We can create all kinds of very interesting shapes. The next one is worked out in a textbook. I'm not going to do that one because you know all the letters and things, you can read it. But I want to explain it, so I'll bring it up on the screen, talk about it, and then go and do more stuff from homework. Look at that shape. Those two edges on top are extremely sharp, all right? What you have is, over here, it was like a tube that has a very thick wall. And now we apply a function that cuts through it. So you still have a hole over here, but now you also have these edges. And the question is, what is the volume of that shape? This cannot be solved in X and Y domain at all. But in this domain, it's a joke. If you look at the domain, it's the ring 2 to 4. So that's your R on the inner side, 2 to 4. It's the full circle, so 0 to 2 pi. It goes like this. Now what's left for the top? Well, we have to have an equation for each one of these, and you see the conversion done. So you can plug that in terms of R's and thetas. You're not allowed to plug in XY equation in. So you have the 2, and then you cut this part out, plug everything in, and 120 pi. So you can read that example. I want to work something else from homework. And then we move to general regions. So when you have the numbers, right, in the limits, well, you are dealing with circles, or circle within a circle, right, the annuals, where we can also have, let's say, a flower, right? It would be cool if we could just 3D print all this stuff, right? If we had a 3D printer over there, you can print your labs in 3D.
It's in a science building.
Yes.
Really?
Mm-hmm. I think we'll have like 10 now.
We can all just use AutoCAD to submit our labs, right? Or Fusion 360.
In virtual reality. All right, so here's a problem for you to enjoy real quick. So you have a hyperboloid which is given as z equals 5 minus the square root of 1 plus x squared plus y squared, and you also have another piece of information, and that is the region R. Region R is r theta, such that 0 is less than r is less than equal than 1, and 0 is less than theta less equal than pi. Can anyone describe this domain to me? What is this?
A half circle.
Half circle is great. Now, half what circle?
Half a sphere.
No, it's not half a sphere. It's a circle. That's 2D. There is 1, 2, 2D. So it's a circle, but look at the numbers. What is that with that circle? It's half of the unit circle. Radius is 1. So it's a unit circle, and it's 0 to pi, so it's only the top portion, right, above x-axis. So your region R is this. We convert z into 5 minus square root of 1 plus r squared. Because x squared plus y squared is r squared, and I need z to be only in terms of r and theta. Now it is in terms of only r in this case, so we can use that. Volume is double integral 5 minus the square root of 1 plus r squared. We have to put that in parentheses because both of those need to be multiplied by a string. We want half of the circle, so 0 to pi, and we want the unit circle radius must be 0 to 1. So stare at this for a second, trying to make sense of it. You have your function that you're integrating. That one needs to be in terms of r and theta, so that's the conversion for it. Your region R goes in the limits of the integrals. Theta is only 0 to pi, r is between 0 and 1. So those are given to you, just plug them in. And now, if you were panicking before, how I'm going to integrate, well, it's a basic U sub, because this r will distribute to both terms. So you will have to integrate 5r, and then you will have to integrate r times the square root. R times the square root you can do in a few different ways. So let's see. So the first order of business is to distribute r. So we have 5r minus r square root of 1 plus r squared, close the parenthesis, dr d theta. The first integral is basic. The second integral is very good. So now that we are integrating, we have 5r squared over 2 minus, and now we use u substitution, so u equals 1 plus r squared, du equals 1/2 r dr. Uh-huh.
2r?
Did you just say 2?
2r. Wouldn't du be 2r dr, not
You
1/2?
can take out the 1/2 so I can't go out.
I'm just testing you. And you all passed the test. Wait, is he plotting another fraud?
Yeah.
Yeah.
Like down thinking it and get up or something.
All right, so what is this integral? It's going to be 1/2 integral of u du. Perfect. So this is going to be 1/2 u to the 3/2 over 3/2. So this dies, and u is the
Plug in for you.
yeah. It's 1 plus r squared to the 3/2. Great. Computed from 0 to 1. I still have d theta. Integral 0 to pi, 5r squared over 2. Oh no, I need to plug numbers in now.
Yeah.
Plug in 1, we get 5/2. Plug in 1, we get 2 to the 3/2. That's 2 root 2 over 3. And 0, everything dies. D theta. So this is 5/2 minus 2 root 2 over 3 times pi. Now you can go get the decimals if you're interested. All right, so now that we are done with the basic setup and basic integrals, we can look at some spicier situations. Every single problem we did so far, as a shadow of the domain, we had a circle, or circle within a circle, right? Now, what happens if you have a flower stencil or a cardioid stencil, right? And I say stencil because I want to see those walls extend up to give me volume, right? So now we're going to talk about the general regions. And the integral for general region would be let me just write this. Okay. So the double integral of alpha and beta on the outside. And now we are going to have two functions, g of theta and h of theta. We still have our f of r theta here, and now we have r dr d theta. Now this will allow for some very interesting situations. (13.3). 13.4 is triple integrals. You'll notice. You'll notice when it switches, you will have 3 squiggles. Yes. As many as you want. Application is 3, but as many as you want. You can. It's linear, so you can chain whatever amount. It's not going to have application, but.
Once we can comprehend shapes in 4D and we want to calculate the area of that, then we have the quadruple integral, right?
Yeah. All right, so now we want to, in addition to what we did in Calc 2, we want to compute the volume of the object, which is the volume of the stencil that you are using. Now, the stencil could be, let's say, a stencil of the moon. Let's say it's good. So now you're looking at this thing. You want to find the area of this, but remember, this is actually a cookie stencil, so there are walls along these black lines coming out of the page, the screen, whatever. Right? So there is a whole structure going out. And let's say that structure on top is again some kind of paraboloid. So let's use z equals 0 for the bottom and z equals this is a bad placing. Leave space to the right, guys. So what was the z? Z was equal to 0. And z is equal to, let's go with 16 minus x squared minus y squared. So the stencil is going to bring those walls straight up, but then those walls will be capped by z equals 16. So it's a paraboloid that starts at z equals 16, and then it goes down, right? And the moon underneath goes straight up. So now you're going to say, well, okay, this sounds a little bit crazy. How do I find the equation for the moon? Well, you fit the shapes inside. You fit the shapes that will the best describe the situation. So you want to have a circle that will describe the inner side, and then that circle is going to have a center somewhere. You are going to now draw a 2-petal flower through this, and when you snake everything through, you get the area you're interested in. Yeah, I did tell you to bring multiple colors, right?
Yeah.
All right, so we are only 4 lines away from Deadpool.
Does the intersection of the flower have to go through the x, y, like at 0, 0?
Yeah, it does.
Okay.
It's just your eyes are terrible, so you can't detect that.
Oh. So wait, what's the t equals 0? I don't get it.
What happened?
Z equals 0.
Z equals 0 is the floor. And Z equals 16 minus x squared minus y squared is the umbrella on top.
Oh, I purposely made it not on the axis.
Your shape needs to be bounded. All right. Okay. To do this, I'm going to draw a representative pizza slice. You're welcome. This is d theta. Why am I drawing representative pizza slice? This is infinitely thin pizza slice. That is d theta. So a separation of the angle, but infinitely thin. I don't know how to do this any other way. As a student, I looked at this and I said, well, there has to be a systematic way that works 100% of the time. And those are your dx, dy, dz, d theta, and so on. Look how easy this is. What is representative pizza slice doing? It's rotating around in a 0 to 2 pi environment. So I need the red part sectioned off. How do I do it? The representative pizza slice is going to start at this angle, and that's my lower limit. It's going to travel through to the bottom part, which would be the boundary intersection, and that one is going to be my other angle. And then I have my alpha and beta. So this angle is alpha, this angle is beta, and those two will be down. I can measure those by simply equaling the two equations. We'll get there. Then I need my functions f. I need the lower limit for, functions r. I need for radius. Now, it's always a lower limit is what's on the representative pizza slice closer to the origin. So circle equation goes on the bottom, and the flower equation goes on the top limit. It's very structured. You can't miss it if you learn how it works. So the first representative pizza slice is going to be at this point here. And that's your lower limit for alpha. It's going to take all of the values all the way up to here and stop, because nothing else is shaded. Stop right there, and that's beta, that angle. And then I have the lower radius r, which is the first one. When you go from the origin along pizza slice, right, you are going to go, I mean, this is the way you eat it, right, I hope. So you will first get to this point and then to that point. So this is the lower limit, this is the upper limit. Lower limit is the circle, upper limit is the flower. So let's put that in. I'll steal the equations and the numbers from the book. Book actually is doing this one over here. It doesn't really matter. So the equations are, circle is labeled as r equals square root of 2, and the flower is r squared is equal to 4 cosine 2 theta.
You're just making those things up.
Yes, those are the two equations. By the way, your job as an engineer, when you are trying to make something that you have to eventually program into a machine to either cut it or into a controller to do something, your job is to actually figure out what are the equations off of the physical prototype object that the artist carved out for you. So forget about easy problems like this when you start working for money. Because over here I give you the equation. Well, that's the reason why for your egg problem, I am asking you to go and suffer until you figure out what the equations are. Because that is the only thing this project that you guys have is the only thing that will make you money later if you want to continue with this 1% cognitive elite deal that you have going on right now. Right? That's your job. You will never integrate because we have computers and software for it. So as soon as you pass your test, 100% of your efforts is on modeling. Right? Because that's the only thing that makes you money. The rest, computers can do better and faster than any one of you and me combined. Cheaper. Right? Computer is what? $500?
No.
And plus a little bit of a software. Wolfram Alpha is free, right? In its base. Come on. You can't compete with that. What happened? Good.
Computers don't get tired or have emotions either.
Exactly.
Yeah.
So your job is to figure out the equations. Now, what I need to do is I need to solve this equation here to figure out what my angle alpha and angle beta are. So we have a cookie cutter that is in shape of the moon, which is flat on the bottom because z equals 0, and it's parabolic on top because it is intersecting with the z equation over there. What's the volume? Well, we are solving now. Square root of 2 squared is equal to 4 cosine 2 theta. We are solving this equation to get alpha and beta. So 2 is equal to 4 cosine 2 theta. Cosine 2 theta is equal to 1/2. And what angles are giving me cosine 2 theta? What angle would give me cosine to be 1/2? Pi over 3, thank you. So, from here we know that theta is equal to pi over 3. You must know this is pre-calc 2, all right? This is 4 courses ago. And there's no way around it. You either know it or you don't. You know, just walk away.
Wait, is that
2 theta equals. From where theta is pi over 6. Okay. So I know that this angle here is pi over 6. If that angle is pi over 6, then this one is also pi over 6 away from here. So that's 6 pi over 6, and this is 7 pi over 6. So what we just found out is that this angle over here is pi over 6. This line will continue symmetrically through this, so this angle must be pi over 6 by geometry. And this is where pi is. So pi, which is 6 pi over 6, plus 1 pi over 6 is 7 pi over 6, and the top must be 5 pi over 6 because you're taking 1 away. Headache, anyone? Good. It's starting to work then.
The other one will be 11 pi or 6?
We don't. Yes, we don't need it, but yeah.
11 pi or 6?
All right. So what's the volume integral? The volume integral for this particular. Now, guys, remember what I told you on Thursday at the end of the lecture. Do not play with fire and mess with symmetry. Now, can you mess with symmetry here? Sure, because this object is radially symmetric. You have a symmetric base, you have symmetric shape on top. So, in this case, still dangerous, but in this case, we can play with symmetry, and instead of computing these guys with limits 5 pi over 6 and 7 pi over 6, we can compute negative pi over 6, positive pi over 6, because this moon and this moon are the same, but the shape on top is the same, and that's the key. That's the key, that the shape on top, right? There is a paraboloid that goes this way, right? So that paraboloid will have the shape, and this will cut the same on both sides. And it's so symmetric that you can actually go 0 to pi over 6 and cut it in two. It's one of the very rare examples when you're allowed to do that. However, if the top was not symmetric like this, if it was some kind of plane that cuts it on an angle, no symmetry there, there will be, if it cuts it on the angle like that, right, so I'm away from the screen, and I'm cutting it into x on this side, there will be more volume here than there, because this will be polar than that side. So we don't play with symmetry in these problems. In Calc 3, don't play with symmetry because it can be very, very tricky. If you don't have a clear, in your head, vision of what this looks like in 3D.
Talking about the d equals 16 minus x squared.
Yep, and the domain too, at the same time.
Just like doubling the volume at the end. You can't do that.
Yeah.
Well, in this case, maybe that's what you're saying?
Yeah. So I'm setting up my integral as 16 minus r squared. That's my z, right? X squared minus y squared, that's minus r squared now. And limits now.
5 pi over 6 to 7 pi.
Yes. 5 pi over 6 to 7 pi over 6 on the outer, because I want the flower thingy on the left. The book has it on the right. I'm using one on the left. And also, book is doing only the area. I'm working on the volume, so you have more here. What else is there? Observe your limits, guys.
Pi over 6 to 11 pi.
Yeah, we're done with the limits, but we have the inner limits now. And those are r equals function of theta. So, what do you hit first? You hit the circle first, so that's a root 2 on the bottom. And then you are hitting the top first, which is square root of 4 cosine 2 theta. All of them. I'm sorry? That's the easy one, by the way.
Yeah.
That's the pizza slice. The pizza slice, remember, starts at the origin. We go up the pizza slice. We first hit the circle. That was the lower limit, right? And then we hit the other one, which is the upper limit. So the lower limit is the circle, which had the radius of root 2. And the upper limit was the flower part, the two-petal flower part, which had r squared equal to, and then you take the square root of that. Was that squared? No, it wasn't. Okay, good. And now integrate. Right? Good luck. So integral 5 pi over 6. And now we are integrating 16r, that's 8r squared, minus r cubed, that's r to the 4 over 4, computed from root 2 to square root of 4 cosine 2 theta d theta. You see, that kills the root, which is good, right? Plug in the upper limit into r squared, root dies, so I have 8 times 4 cosine 2 theta minus, well, now we have to the fourth, right? So it's going to be 4 cosine 2 theta squared over 4. So that's when you plug in square root. Then we have minus square root of 2, that's going to be 8 times 2. Minus and minus give me plus of square root of 2 to the 4th over 4 d theta. And we got this. 5 pi over 6, 7 pi over 6. So 8 times 4, that's 32 cosine 2 theta minus. Now over here, I have 4 squared 16 cut by 4 is 4. Cosine squared 2 theta minus 16 plus 2 squared squared, that's 4 divided by 4, that's 1 d theta. Right now, you can't integrate because of the square. How do we integrate cosine squared? What's the only way? Yes, power reducing formula. There is no way, there's no other way. So cosine squared x is 1 plus cosine 2x over 2. You either know it or you walk. That's that. Well, no, there's a way with power series, right? You can expand the cosine of the power series, keep the 4 terms, then square the 4 terms. No? Then remember the formula. So 5 pi over 6 to 7 pi over 6. And then we have, so 32 cosine 2 theta minus, now 4 will kill 2, I still have 2 left. 1 plus cosine 4 theta, because we started with 2 theta and you have to double it. And then minus 15, and then d theta. Whew. All right, so this is going to be the no, it's annoying, it's not spicy. You can find some spicy problems in the book. Cosine 2 theta. Minus 2 minus 15 is minus 17. So I have minus 2 cosine 4 theta and then minus 17 d theta, and we can finally integrate. So this is 7 pi over 6. And no, I don't need this. I'm integrating. Guys, derivative integral of cosine is positive sine. So I have 32 sine 2 theta divided by 2. That's from the u sub, from the 2 theta. Minus 2 times sine of 4 theta divided by 4 minus 17 theta from 5 pi over 6 to 7 pi over 6. Nice. That's 16 sine 2 theta minus 1/2 sine 4 theta minus 17 theta. From 5 pi over 6, who picked these numbers? 7 pi over 6. Great. Now I need to plug these guys in. 2 will kill the denominator of 6, right? So I have 16 sine 7 pi over 3 minus 1/2 sine of 2 will cancel, so 14 pi over 2. No, 14 pi over 3, right? I have 14 pi over 3, yes. 14 pi over 3 minus 17 times 7 pi over 6. Minus the lower limit, that's going to be 16 sine of 5 pi over 3. Now minus and minus is going to give us plus 1/2 of sine of 10 pi over 3. 4 times 5 is 20, and then 20 and 6 cancel to 10 pi over 3. And then plus 17 times 5 pi over 6. Woo! I don't need these parentheses, just compute this. All right, unit circle. I need pi over 3. 1, 2, 3, 4, 5, 6, 7 pi over 3 is the same as pi over, so 7 pi over 3 is the same as pi over 3, so that's going to be 16 times root 3 over 2. Nice. Minus 1/2 sine of 14 pi over 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Next one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes, next one. So 14 pi over 3 is going to be here, but it's also, so it's same thing. Yes, good. Minus, I'm going to deal with numbers later. No, it does. You have the two of these. So you factor out 17 over 6, right? When you are dealing with these numbers, you factor out 17 over 6, 17 pi over 6, and what's left is 5 minus 7, that's negative 2. That's what happens. I gotta move this. And now, I'm going to lightly circle these. And then I have minus sine of 5 pi over 3, so minus 16. Sine of 5 pi over 3, so 1, 2, 3, 4, 5, negative root 3, thank you, over 2. And then plus 1/2 of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, also negative. Root 3 over 2. Woo! Tons of fun. This is 8 root 3 minus root 3 over 4 plus 17 pi over 3. Minus and minus gives me plus 8 root 3. And then minus root 3 over 4. So this is 16 root 3 minus root 3 over 2 plus 17 pi over 3. 16 minus a half is 15.5. So that's 15.5 root 3 plus 17 pi over 3. Equals to some number that you can get if you are in love with decimals. And that's 13.3. So please, next time when someone tells you, what do you know? Woo! A simple problem that takes 30 minutes to do. Good. So let's take a short break. When we come back, triple integrals.